home. And I don't know what your biggest holiday is in India, but also it's a bad thing. Better. No, but you really have to love it because as you become higher in the hierarchy, there are more things that will distract you. You know, you become a chair, you have family issues, you have a lot of things going on, and unless you love your project so much, you stop science. And so that's why I think your thing. And so asking your question, what's more important, clinical or bench? It really, the importance comes from you. If you are satisfied by clinical projects, go for it. If you are satisfied by basic science, and to be honest, in my experience, the NIH pays my research much more money if it's very basic than if it's clinical, you know? So, and the reason is, if it's clinical, they always tell me, oh, but you know, you don't understand patients enough and things like that. So for me, bench science is always the answer, but for a clinician, often bench science is not the answer. Yeah.
Which has more impact? Which has more impact in
the same thing is the same answer. The more you love your project, the bigger your impact. And it doesn't matter whether it's in the bench science or it's in the clinic. Really, I mean, the impact is from you, you know, and you can turn any project into gold if you love it. And so, but you have to find that. And I tell you, you don't know it until you do it. Like I wanted to be an ecologist. I loved, you know, ecology, the rainforest, etc. But then I did ecology and it was boring like hell for me, okay? And then I said, oh, what, you know, this is terrible, I want to be a geneticist. And then I did genetics and I kind of liked it, but I noticed that after 6 weeks of pipetting and getting then a black band that was stronger in Western blot, it wasn't exciting for me enough. And so I decided not to be a geneticist. And then I sticked an electrode into a brain, and I heard brain activity, and I fell in love in this brain activity, and this love never went away. But if you would have asked me 20 years ago, Nino, do you want to be a neuroscientist? And I would have told you, this is the last thing I want, because I don't want to kill animals, I want to go into the jungle, I think it's important. But my true love is in the brain, and I tried everything else, like ion channels. I love electrophysiology, but my friends in my team, some love genetics, some love CRISPR approaches, some love molecular biologists, and the key is that you mobilize this love to form a team. So you have to find it yourself, because I have one student. She loves animal protocols. She loves all these regulations and the policy. So she's a born person that does exactly the things that I hate to the guts, you know? And so you have to find this. I had a student that she came to me, Nino, I want to study consciousness, okay? And I said, oh my God, consciousness, this is a really big issue. And she says, yes, I love consciousness. I really want to find the mechanism of this. And I said, oh my God, I'm only interested in rhythms, but let's start the project. And then it turns out she loved pharmacology. She was my best pharmacologist. She put drugs on everything and just got hooked up by this and forgot about all her consciousness ideas. So, and so you don't know, you know. And in fact, you know, sometimes you find frustrated scientists. And these are the scientists that didn't find what they love, you know. They, like, for example, I totally believe in climate change and that we have to be, you know, good to Mother Earth and be environmentalist. But if I would have been someone who works for environmental protection, I would have gone crazy, because I had to fight with politicians, and I would have fought all the things that don't turn me on, you know. So basically, I did not go what I think was important, because it's not me. I hate all that stuff, and so that's why I think you have to find it, what you love it, and I mean, it's the same thing. I mean, you cannot marry every woman. You have to find the woman. And you have no clue why you love that particular woman, you know? And sometimes you doubt.
You think who got Nobel Prize? There are basic scientists.
Yeah,
They never got prize or anything like
No, sir, for early scientists, earlier
that.
research.
You wanted to have the impact. No? Impact comes by recognition. Recognition in any part for that matter. If you analyze who are Nobel Prize winners in medicine and physiology, most of them are on basic science.
yeah.
Basic sciences.
But as I said, I have a lot of clinician scientists that basically, they don't care about the mechanism so much, they love the clinical problems. In fact, I had one clinician and one basic scientist studying a similar project in my lab. And it was about asking the question, what calcium channels do in generating the respiratory rhythm. So Frank was a basic scientist by heart. He only cared about the ion channels. And so each time he recorded, I said, hey, Frank, is this a rhythmic neuron? And he said, oh, Nino, I didn't check. And then he checked, oh, it's not rhythmic. But he wouldn't even care whether it's rhythmic, because he didn't care about breathing. He cared only about ion channels. And to this day, he doesn't care about rhythms. He cares about ion channels. And the other person, the same project, he only cared about rhythms. And because he was a clinician, he wanted to understand, how does it cause arrhythmia? And so he didn't care exactly how good his calcium channel recording was. You know, like Frank always said, my God, Bernd, you cannot use that recording, it's shitty, you know, don't you see all this leak currents? And he said, what is a leak current? You know, so basically the combination was great to have these two, because one cared about the channel and the other about the question. But for some reason, they didn't care about the other thing, that they were not involved. So that's where you're, as a principal investigator, plays a big role, because you combine these two people, because you cannot change them. I mean, Frank will never care about the rhythm, but he always cares about ion channels, to the extent that I don't care about it, you know, so. And to be honest, I can see that Kusal has the same strategy in his lab. Because that only then you have a dedicated lab. You know, if you find personalities, and as I said, I expect from my people that they are better for what they do than myself, because, you know, Frank knew way better about calcium channels than I, and Bernd knew way more about the clinical implication than I. So it's also another important lesson is, never think you're the best, you know, because really your people are the best, and if you don't attract the best people, you will also not be successful. So in a way, I'm just the messenger of their creativity, and that's the trick. And by the way, that's also why I can be here in India, but my entire lab works. And so when I come back, they bombard me with great new data, and so I feel very spoiled. And actually, another important lesson is that sometimes it's important that you do your own experiments after a while. Like I get so spoiled, but when I do my own experiments, then I realize how hard it is. And I sometimes forget how hard it is, you know? So when you say, it took me 1 year to develop that preparation, that's so normal, you know? But if you're too detached, then you say, what? It took you 1 year? Are you lazy? Are you crazy? No, it's normal. So you have to always know that it's normal.
Yeah, it happens. Actually, many people, they could not understand, because they have to present every 6 months in front of the PhD committee, their progress report. And they have no progress, because they failed.
Oh my God, yeah.
Yes. So they are demoralized, and then my role was as a supervisor to make them correct and give them support in that.
Kusal, this is something like, I have a very talented cardiologist, and she basically got 2 years of free free time from cardiology. And so her committee always says, hey Nino, why doesn't she have a publication after like half a year? I said, well, it takes long. You know, it takes way longer. So I go at each committee meeting, I go with my cardiologist to the clinician to defend her because they have no idea how long science really takes. And so I have to always say, you know what guys, often it takes 1 year before you find your project. And then, you know, sometimes a thesis can take, let's say, 2 years before you even, you know, start collecting data. And that's also normal. And here's also one trick. Okay, so one trick that I find. When you have a graduate student, I can put them often on high-risk projects. Because for a graduate student, the time is not ticking. You know, they're not famous yet. Nobody says, what, you haven't published yet? But because the time is not ticking, you can give them much more risky project, but also much more rewarding. Because once they establish a model, which takes a long year, then they can work on this for the rest of their life, and they basically did something high risk, but high reward. Now when I get a postdoc doesn't have time. They have to produce literally after 1 year a paper, because otherwise, you know, they don't get a fellowship and they don't get a professorship. So I put postdocs on much more safe projects, you know, where I say, okay, you're in electrophysiology, you know electrophysiology, I give you a project that will work, but then I give you a second project that takes longer time. So that we call it the bread and butter project, which yields results, and then the high-risk project that maybe gets us into a nature paper or something. So we always combine this, but it's a practical trick from a PI to know what to expect from a graduate student and what to expect from a postdoc, you know. And postdocs usually come with a lot of knowledge, and so you first capitalize on their knowledge, so they produce something. Because the worst thing is if a postdoc after 3 years gets only one paper, you know. So that's, whereas a graduate student after 3 years, one paper is good. Yeah.
Let me. And you know, I think that, for instance, I went to, when I finished, when I became a medical doctor, my father sent me to the University of California in San Diego to spend a couple of months there. And I met David Wilford. He was a fine guy, and he taught me a very ingenious technique where you used yeast cells and you put a tryst buffer on them, and then you oxygenate them a lot, and you put it on an oxygen electrode. So you started seeing how they consume oxygen, and it was a linear decrease like this. It was going down, 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 very linearly until no oxygen was present in the solution. Then you put in some amount of blood, which is microliters, and then you oxygenate again, and you put it all again in the electrode, and it starts going down from the high oxygen concentration, like 200 millimeters of mercury, and then suddenly you see that it isn't no longer a line, but it's a curve, and it extends like that. So that's the oxygen dissociation curve. That was a beautiful thing. When I saw that, when he taught me that, I said, this is fabulous. I have to take it to Bolivia. He said, sure, I'll give you a tryst buffer. He gave me the buffer, and I took it back to Bolivia, and we started doing oxygen dissociation curve. That was a beautiful thing. And it gave me great satisfaction, because with that I showed, for instance, we showed with my father that in chronic mountain sickness patients, people that have high hemoglobins, you saturate it, again, you do the technique, and instead of having a curve like going like this, it goes way over there, because there's so much more oxygen, because there's so much more hemoglobin, which means that the hemoglobin is perfectly functional. It's not that there's an alteration in these cases of the hemoglobin that would sort of explain the more red blood cells being produced. So that was very interesting. But the reason I'm telling you that is because later on, after several years, I asked for, how's David Wilford, this kind guy? And they told me, oh, it's very sad. He committed suicide. And I was shocked. And I said, what? And then you come to think of it, you see science can be frustrating. Because if you are dreaming of making a great discovery and you just can't come up with it, and he made these fabulous papers, but somehow something went wrong, okay? But I then went on many years later to be a visiting professor at the University of Copenhagen with Professor Paul Erik Paulo. And he explained to me that actually science was the joy of seeing the light. That was his farewell speech from the University of Copenhagen, where he was 50 years a professor of physiology. He said, it's a matter of feeling the joy of seeing the light. In the end, when you do an experiment and you think and you have a hypothesis and you see something that nobody else may have seen, it's a wonderful joy. But I think one shouldn't worry, will I get recognition for this? Because that's an issue. And sometimes recognition doesn't come in 10 years or 20 years, you know. And so I've even, in fact, in physics, there's one of the great chapters of physics is about a guy that talked about the molecules. I don't remember his name right now, but the molecular movement, he developed a formula, and everybody attacked him. Everybody, all the physicists, the major physicists said, oh, this is ridiculous, this is crazy. And he went with his family on vacation, and he stayed at the hotel and hanged himself, you know. But then a little time went by, and his paper became the top-notch paper. So don't get frustrated. Enjoy the joy of seeing the light with your experiments. Like Nino says, find it, what clicks, and don't worry about the rest. Just do it. Be certain of what you do, and give it time. Give it time. And of course, enjoy the rest of the other things like families, you know, and friends, and visiting Kusal Das, and leaving all my job, and then working really hard when I go back. That's it.
There's another part of why it's important that you love your thing, because we often find things, we often have results that conflict with how people think at the moment. So you break dogmas, and you create enemies, and this happens a lot. You know, like I had Tatiana, so she discovered a new form of breathing, and I said, Tatiana, you realize that people will hate you for that because they think totally differently. And then Tatiana said, Nino, I want that they like me. I don't want that they hate me. And I said, Tatiana, you know, you cannot avoid it. You are breaking people's career with your new discovery. And then sure enough, we published it, and people hated her results. And but at the same time, we knew we had made a new discovery. But we love this discovery because it brings us further. But often you find controversies, and that's why I think we heard this several times. In science, you need also courage, you know, because often finding new things are controversial, and sometimes you're wrong. Like I mean, I also made some mistakes where I was fighting for something, and it turned out to be wrong. So I think that makes a scientist also humble, because you know, you're trying to find the truth, but often, you know, you get misled. But 90% of the times when we find something which we don't understand, it becomes more interesting. So often when you don't get what you expect, that's the beginning of great things. So each time a student comes to me totally disappointed, says, Nino, it didn't work, look at that, totally wrong. Then I say, wow, fantastic, great, let's go on. So it's about finding new things, and finding new things is always first shocking, okay? And people will not like it, but that's part of the job. Okay.
Okay, sir. Myself, I am Satish Patil. I am a physiologist. So actually, we met in the morning.
Yes, exactly.
And we had few discussions. So just in 1 minute, let me say what I
Yes, exactly.
did,
Yeah,
and I wanted to know the facilities at your institute. So I'm interested, as I said, that I'm interested in working yoga and meditation physiology, but mainly focusing on the cardiovascular health.
Fantastic.
And I'm more interested in the mechanistic studies.
Yeah.
Okay, when you a particular technique, when you practice, then how actually it benefits, the mechanism of benefit. So step by step, for example, for the first time when we saw that a particular breathing technique, it reduces the blood pressure, then I was interested to know the mechanism. What is the link between these two? Then next we found that, okay, in the next study somewhere the sympathetic overactivity decreases. Okay, but again, how it happens, we don't know. How it reduces, we don't know. Then we thought of, okay, there might be some decreased oxygen consumption by which a study that hypoxia is. There are two types, as you said, again, always there are two groups. One group says hypoxia is not good, another group says hypoxia is good. So here in the meditation and this yoga, usually we reduce the respiratory rate and so that oxygen consumption is less, and we hypothesize that, okay, there might be less oxygen consumption, due to that there is less oxidative stress and that might be beneficial.
Yeah.
Then later we thought that, okay, this sympathetic overactivity may be decreased and due to which the vascular tone is decreased and the blood pressure is reducing. Next we thought of, okay, what is the role of the endothelial system here? Then we got one paper where we found that, okay, in the coronary artery disease, the endothelial function improves. Then again the question is same, okay, how it improves? By practicing this, how it improves? Then we thought of assessing various molecules of these endothelial cells. What happens? The interplay between all these molecules which the endothelial cell secretes. And recently we have just completed one yoga-based cardiac rehabilitation program on the acute MI patients, acute myocardial infarction patients, where actually we were thinking earlier of that there might be some improvement in the nitric oxide levels, but surprisingly for the first time in this gathering, I'm telling you because they are not published, but we found there a decrease in endothelin 1 level, a great vasoconstrictor. But same again in my mind, okay, if this in slow breathing and all those things, how it actually it is called? It is modulating. How it is modulating the endothelial cell products. How that beneficial changes are taking place. Then suddenly in the morning when I heard your lecture, so it triggered, now number of questions are there in my mind since from the morning. So where you have shown your slides in the morning, when you now just took a sigh, then I am seeing firing of your neurons in your brain.
Yes, yes, yes.
So when you show that different breathing levels, as you said that everywhere are different clocks and different breathing levels, it fires different neurons. Now, okay, now that coupling somewhere, okay, where now which types of neurons actually in different practices, different techniques, what are those different groups of neurons which are actually modulated?
Yeah, yeah.
So that will be now, I will not go in detail, the idea what I want to, I'm looking for, that I can discuss it later personally. But thing is I wanted to, ideas cannot be shared at the beginning. So I wanted to know the facilities at your laboratories that in the humans especially, when the humans practice some different techniques, then at the same time or immediately after that, the different areas of the brain, which part of the brain is more firing or less firing, actually different parts of the areas of the neurons are modulated in this one, and which are related to actually different parts because there are different regulatory centers which are there, whether actually it is in the regulatory center or through some mechanism.
Yeah.
So that I wanted to know from you. And really let me thank you as well as our institute. After that morning your
We
talk
are actually
was
having the plan for going with the collaboration.
yes,
Yeah.
that has triggered my mind.
You know, first of all,
these things.
We are going
I am
for
so fascinated the research you're doing and the observations you have. And but I want to disappoint you right away that one of the problems, first of all, we don't do MRI in my lab or my institute, in fact. We always wanted. Secondly, the other problem is that the critical areas don't show up very well in the MRI. Like PAG, maybe a little bit, but in the brainstem, you almost don't see anything. So I think MRI will not, at this stage of science, will not provide you with the right answers. But what could be done, in a way, is to record from, for example, from sympathetic activity, because often people say, oh, it's probably more sympathetic drive or it's more parasympathetic, but indirectly. So maybe one thing that could be done is to measure actually, is sympathetic drive increased? And then deduce from this some mechanism. And how I think at the moment, okay, so my hypothesis, which can be totally wrong, as I said, but we think that breathing consists of different phases, and that every phase is generated by different areas in the brain. So I focus very much on pre-Bötzinger complex, which is inspiration only. So the inspiration sigh is all pre-Bötzinger complex. But there are two other areas. The other area that we just discovered, that was Tatjana that found this area, is the post-inspiratory complex. And what I mean with this is, breathing has three phases. So I take a breath, and now my mechanical recoil forces of the lung want to get air out. But I don't want that air out goes so fast. So what I do, I keep my diaphragm active, and also I activate a lot of my laryngeal muscles and upper airways muscle to slow down the breathing until I run out of air, and then I take another breath. And so each speech I do is during post-inspiration. And this area is controlled by another center than the pre-Bötzinger complex. And it's also the one that you use for breath hold. Okay, so you take a breath and then you activate this area. So when you think psychologically, these two areas are connected with very different characteristics. Inspiration is always like arousal. It's like you say, I'm inspired, I wake up. You wake up with a sigh 90% of the time, like, and so I think that all of this is activating like cholinergic drive and adrenergic drive, whereas post-inspiration is much more introspective. Like when you want to shoot with a bow and arrow in a target, you hold the breath, because that's when you're calm and you can focus, etc. And then you release it, and then you start breathing. You don't do this, So I think different areas are associated with different qualities of your brain state. And so I think what you do in meditation, you actually use these different qualities to change your brain state, and they are associated with different neuromodulators. And what we do now is look in obstructive sleep apnea, where you get hypertension. To what extent does the pre-Bötzinger affect my parasympathetic drive, whereas the post-inspiratory complex affects my sympathetic drive? So when I have this framework in my mind, I'm thinking if you do a meditation that increases your sympathetic drive, it could actually come from the post-inspiratory complex. That basically you're focusing, you're breathing out very, very slowly, and that actually might activate your sympathetic drive. And so what I would think, how I would approach your question is really to characterize exactly your breathing, in what phase is doing what exactly phase you increase during meditation. We all know it's deeper breathing, but is it mainly inspiration? Do you have a more exaggerated post-inspiration? And once you know this, then you deduce out of this what are these different centers doing and how can they control it. So that would be my approach to this question.
I just want to ask you that as you were working on the pre-Bötzinger complex, so in that area when it's on inspiratory drives, and it takes really 3 to 5 milliseconds for each one of to complete.
Yeah.
So whether this 3 to 5 milliseconds, where the channel, ionic channels definitely might have altered.
Yeah.
Whether this time the inspiratory drive are being influenced by certain other neurochemical substances.
Oh yeah, exactly. Oh my God, yeah. I could